128 milliliter, and I want this in, what did I say, in microliter. Yeah, and some people found this a little bit tricky. Now what I'm going to show you is an incredibly useful tool to do these conversions. Many of you probably already know this tool, so it's a revision, but for others it might be a revelation. And I use this tool all the time. There's not a single day that I don't use this tool. And the technique is called dimensional analysis. Have you ever heard that? Few people not. Now, the important thing for dimensional analysis is that we make... Do I have these microliters anywhere? Yes, I've got the microliters here. So what I do is I just simply write it in a way that these microliters here, this unit here, microliter, is on top of this line here. Yeah? So I write 1,000 microliter in 1 milliliter. Okay? Now I've got my microliter up here, which is good because this is where I want it. But I have this annoying milliliter down here. So what I can do now is I just simply say times. Now I want to get rid of the milliliter that I have down here. And what I do is just simply cancel out the units. Do I have a milliliter somewhere else? Yes, I have a milliliter. In my given, I have milliliter up here. So I write 128 milliliter. And you see something magic happens. The milliliters cancel out. What unit is left? The microliter. What do I want? Hee-hee. Right? So all I have to do now is 1,000 microliter times 128. And that gives me 128,000 microliter. Yeah? And of course I can write this a little bit nicer. I can write this in a scientific way. And for this scientific conversion, I just simply move the decimal points. So it's 128,000. So I have the decimal point here. Right? And all I need to do, if I want to get this into scientific notation, is I move this decimal point 1, 2, 3, 4, 5. So I have 1.28 times 10 to the 5 microliter. Of course, I can do that with the nanoliters as well. So if I've got 128 milliliter, and I want this now in nanoliter. So I know that 1 milliliter equals 1,000 microliter, and 1 microliter equals to how many nanoliters? 1,000 again. 1,000 nanoliter. Yeah? Do you want to try that yourself with this wonderful method? Yeah? So I give you a couple of minutes so you can try that. How you do that? So what you simply do is, okay, what do I want? I want my nanoliters. I want to convert that into nanoliters. So do I have in my given anywhere nanoliters? Yes, I do. I have 1,000 nanoliters in 1 microliter. Nanoliters is good because that's what I want, but the microliter is a nuisance. So let's try to get rid of the microliters. Now, I know that I have 1,000 microliters in 1 milliliter. Yeah? So I see already the microliters, the units cancel out, but I still have the milliliter there. So, in order to get rid of the milliliter, I know that we've got 1,000, do I have milliliter anywhere? Yes, I've got my, what's given here. So I put that in here, and I have 128 milliliter. And what I see is the milliliters cancel out again. So I have 128,000, that's this one here, 1,000 nanoliter. Yeah? Does that make sense? And if I want to do it in scientific notation, how often do I have to shift the decimal? 1, 2, 3, 4, 5, 6, 7, 8. So I've got 1.28 times 10 to the power of 8 nanoliters. Does that make sense? It is easy to do this. There's a slight issue. If I, for example, have 128 nanoliters, and I want to convert that into a milliliter. So we're doing the opposite now. Again, I know that 1 milliliter equals 1,000 microliter, and 1 microliter equals 1,000 nanoliter. Okay? Okay, what do I want? What is the unit that I want? It is milliliter. Now, do I have milliliters anywhere in my givens? Yes. I have 1 milliliter, and that equates to 1,000 microliters. Yeah? That's from here. And because there is this equal sign here, at this point here, I can turn it around in the way I need it. So I've got my milliliters here. That's good, but I have these annoying microliters down here. So what can I do? Well, I can get rid of these microliters. And I can say I've got 1 microliter in 1,000 nanoliter. That's this part here. What happens to the microliters? They cancel each other out. So I have got milliliter here, but I've got the nanoliter down here. I don't want the nanoliters. So I just simply say 128 nanoliters. And you see, the units cancel each other out again. So what I have is 128 milliliter. That's the unit that's left here. That's the unit that I want, divided by 1,000 times 1,000. Yeah? Does that make sense? So how do I write this? Well, I can write it as 128.0. And then what I can do is so here's my decimal, that's my 128. And now I put zeros in front of it. 0, 0, 0, 0, 0, 0, 0, 0, and so on and so forth. And now I count the zeros that I have at the bottom of my fraction. So we've got 1,000 times 1,000 gives million. So this is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So I place my 0 here. So that would be 0.000128 milliliter. Have I done it right? You were counting? Checking? That's good. Never trust what I'm saying. Okay? Are you happy with that? This method. This is a very, very simple method, but we will use this method when we come to molarities and concentrations and things like that. And you will see a lot of people, probably in their chemistry lectures, have learned equations. The molecular mass of something times the volume of something and something times the square root of God knows what. All these complicated things. Of course you can use it. No problem. But this method, you don't have to use any, you don't have to learn any equations. Right? So that's a really nice, neat little trick. Are you happy with that? Obviously, you need to practice, and you will get a lot of practice, trust me. But if you haven't done the numeracy stuff yet, which is due next Friday, is that right? Yeah. Do it as soon as you can, because then I still can help you overcome any problems with that. I monitor it constantly, and I can check out what do you know, what you don't know. Okay, happy with that? Okay. Right. Now, another thing that people told me, or that I have seen, where people have a little bit of they don't find it easy, was the statistics part. And I told you, I hate statistics. You probably hate statistics, so we've got something in common here. But unfortunately, it's a very important thing that we need all the time. Now, we have basically two ways to look at statistics, what we want to do with statistics. And the first thing is that we want to describe data sets. Describe data sets. Now, these data sets can be very small. It could be, say, 3 data points. Or they can be massive. It could be your entire genome or something like that. And if I just have 3 data points, it's not terribly exciting to do a description of that. But if I've got, say, 20,000 data points, then nobody wants to troll through this. I just want to know what's the important bits about these 20,000 data points. Yeah? So this is called descriptive statistics. Well, just simply describe certain data sets. The other thing where I want to use statistics is when I want to see the big picture. And for example, I am a manufacturer of onesies, right? And I want to get it right. I want to maximize my profit. So what I'm going to do is I will try to produce onesies in the right size so that a maximum number of people are going to buy these onesies. Right? Now, if I make these onesies too big, then it's not good business because I lose material. If I make them too small, then people don't get into them and they won't buy them either. So I have to get it right. Now, in order to get them right, of course, ideally, I want to measure every single adult in the UK. Because then I know exactly how big I have to produce them. But very clearly, this would not be terribly practical. So what I do is, I just simply measure a small group. So here, that would be the entire population of the UK. But I can't measure them. There's 60 million people in the UK. Can't measure them all. So what I do is I take a sample of that. So that's the population. And that here is a sample. So what this kind of statistic is doing is it uses a sample which then allows me to make conclusions about the entire population. It allows me to make inference. And that is why this kind of statistics is called inferential statistics. Yeah? So, for example, I can do a little survey. Who watched Coronation Street last night? Anyone watched Coronation Street last night? Who watched the football last night? Hands up. 1, 2. Okay, so we have about 150 students here, and 3 students watched football. Now, from this knowledge, I can try to figure out how many people in the UK actually watched football. Yeah? So I can, from this sample, from this little survey, I can roughly calculate how many people watched football. So this is the difference between descriptive and inferential statistics, and also I showed you what is the difference between sample and a population. Now, let's go a little bit back and say to descriptive statistic and say, okay, what can I do with this descriptive statistics? So, for example, I have a set of data. Let's say I measure the number of colonies on a plate. So I've got, on the first plate, I have got 5 colonies, then I have 8 colonies, and then I've got 17 colonies. Yeah, so I've got 3 samples, and this is my colony count. Now, of course, I can now describe that in a paper and can say I've got on the first 5, 8, and 17. Which is all right, because it's a very, very small number of plates. But if I have 30 plates, for example, people will say, oh, can't you summarize that? And that's why we have certain ways of summarizing data. So what we can do, for example, is we can define the mean, we can define a measurement of central tendency. And for this central tendency, I basically asked the question, what is the easiest way to summarize these data? And you've heard about the mean. Can you quickly calculate the mean for me? That's the average. 10? Is that 10? Yes, you are absolutely right. The mean is 30, so it's 5 plus 8 plus 17 divided by 3, and that gives 30 divided by 3 is 10, exactly. So that's a very good way to describe this group of data. That's the mean. There's another way of describing it, which is called the median. Median is 8. So the median is 8, it's the middle number. Yeah? Which is better, mean or median? Sorry? Mean. Right. Are you sure? Okay. I do now another plate under the same conditions, and I get 1,000 colonies on it. What's the mean? It's 1,030 divided by 4, isn't it? Loud.
The mean will be bad because we have 1,000 added onto it, which means we will have a way over 17, but under 1,000. But the median will be between 8 and 17, will be in between the different samples.
Absolutely right. So just for the last row, in this case, the mean would be, huge. It would be around. It would be 257.5. Yeah, 257.5. That would be the mean. But the median in this case would be between 8 and 17. So it would be halfway between 8 and 17. So that would be 12.5. Yeah? 12.5. So the advantage of the median is that it is resistant to outliers. So if your data are within a certain nice range, then by all means, use the mean. Pun intended. But if you've got a wide spread of data, then we run into trouble. Yeah? Now, how do we measure this spread? If we just simply ignore this 1,000 now, what we can do is we can measure actually how far each data point is away from the mean. Yeah? So, and this is called a measurement of dispersion. So we measure simply how dispersed, how spread out our data are. So we have 5, 8, and 17. And what we do is we measure how far they each are away from the mean. The mean was, and I write it like that, mean, that's an X with a little dash on. That's usually average or mean. The mean was 10. So I measure 5 minus 10, 8 minus 10, and 17 minus 10. Yeah? 5 minus 10 gives minus 5, minus 2, 7. Bless you. Yeah? Now, when I add them up together, what do I get? I would get 0. So it would say to me, oh, there is no spread in the data because there is a 0 spread, right? It's a little bit, no, I don't believe that there is a spread. You can't do that. But what can you do in order to make a minus disappear? You square it, exactly. You can't do that with your bank account. But mathematically, you can do that. So you can square everything. And then you can sum it up. So minus 5 squared, that gives you 25. Minus 2, that gives you 4. And 7, that gives you 49. And now you can sum it up. What does that give you? 78. So that's the sum of the square of the differences between the data point and the mean. Blimey, that's, if you roll that on the tongue, that's quite a feat. The sum of the square of the differences between each data point and the mean. If you try to explain that to somebody, they fall asleep. Yeah? And what we want to know is, how does that fit into the entire picture? Is 78 big or is 78 small? We don't know, actually, at that point. But what we can do is we can divide this 78 by the number of data points that we have. Yeah? So we can divide 78 by 3. And that gives us 26. Thank you very much. This is 26. So this is what is called the variance of the data. The variance of the data is you take the sum of the squares of the and divide it by the number of data points that you have. Yeah? So that's the variance of our samples, of our data point, I should say. But usually people, if you look at it, I told you things always have a dimension. This one here would have colonies on a plate, the dimension. So that would be colonies. That would be the unit. But now here, this one here, this 26, has a very bizarre unit. It would be colonies squared per plate squared. Well, you can have square plates, but what on earth is a squared colony? You can't do that. So that's why people invented the trick of saying, okay, I've got my variance, but because of this unit malarkey, I just simply take the square root of the variance. And the name for that is standard deviation. So if I do that here, so the standard deviation for that would be square root of 26, and that is something along 5. 5.09. 5.1. Yeah, something like that. So that's my standard deviation. And now all of a sudden, because I've got the square root in, I can say it's 5.1 colonies per plate. My units are sort of intact again. Yeah? So that is a nice description of my data here. 5, 8, and 17. That's, if you like, that's my population of the data. That's my population of this result. So that would be the descriptive statistics. Now, let's say each one of you has done that, has done this experiment, and has produced 3 plates. Right? Now, I'm inherently lazy. I really have better things to do with my life than count all of your colonies. This would be 600 plates, and I would probably hit the bottle after 100. Yeah? So what I do is, if I want to know how many you've got on average, what I do is I just simply take a sample. Yeah? So, if I might have on my sample, in my sample I just take 3 plates, I might have 5, 8, and 17 again. Yeah? Just for convenience. This could be the number that I just simply pick in these 3 plates. Now, can I use the sample to estimate what is the mean? What would be the average of all 600 plates? I do exactly the same thing. It would be 10 again, yeah? So the mean would be 10 again. I could even calculate the spread. But there's a little issue there. Because with the spread, I need to be careful. If I, for example, just simply by chance pick a plate with the lowest number that occurs here amongst the 600, and this is 5, and 17, that's the highest number, then I can very easily calculate the spread. I just do it like I've done it before. But unfortunately, this chance is not very big. So when I take a sample like that, does it reflect the correct spread? Probably not. Do you expect that the spread will be larger or smaller? Let's be on the safe side. It's probably larger, the spread. Yeah? There might be people who have 1 colony on it. There might be people who have 15 colonies on, have 25 colonies on it. So probably my spread is larger. So I calculate my squares, and that was 78 again, so squares, 78. Now for the variance, our variance earlier was where we said we take this 78 and divide it by 3. Yeah, that was earlier. What we now do is we do a little dirty trick. It's like eye gouging in rugby. We also divide it by the number of data points that we have, but we take away 1. We divide it by n minus 1. So 78 divided by 3 minus 1. Yeah? And that gives us 78 divided by 2, that gives us 39. With this simple trick, where I just take away 1 of the data points, with this simple trick, I have increased my spread. Yeah? Before, it was 26.5, was that right? Yeah? Before, it was 26.5, No, it was 26. Now it is 39. This is just to be on the safe side. And of course, I can do now the standard deviation. I abbreviate standard deviation in the way that, for example, Excel spreadsheet program is using it. And I do the square root of 39, and that gives me 6.24. Yeah? So, before, when I just simply summarize the data, my standard deviation was 5.1, the spread, and now the spread is 6.24. It's wider. It's not dramatically wider, but it is wider. What have I done? In this example here, I used my data points as a sample. So, as sample, to get a picture of what you all did. Sample for population. Yeah? And therefore, this trick with the n-1, therefore, is the sample variance and the sample standard deviation. So sample, variance, and standard deviation. That is n-1, because I want to be on the safe side. When I look at this example here, I don't want to know the big picture. I just have these data points. So that is my population already. So that's population. Okay? So what I have here is my population, variance, and standard deviation. And you see, population makes use of n. Sample makes use of n-1. And you can remember that very easily by thinking a sample is smaller, so it's n-1. Does that make sense? Yeah? Do you want to try that with the quizzes again? Because hopefully, with this knowledge, you now can do very easily, what is the population variance? Well, I divide by n. What is the sample variance? I divide by n-1. Which one are you going to use when you do experiments? Well, that depends on what your question is. If you just want to summarize your data, you just use a population. If you want to know how your sample fits into the others, and if you want to get an idea about the other, then you use the standard deviation. Does that make sense? One last thing that is a little bit like Steve Jobs from Apple. One last thing, one very common measure of dispersion is also the standard error of the mean. And what this is, we had just, let me just check. We had our standard deviation, our sample standard deviation. Was 6.24. That is what we just calculated. Now, and our mean was 10. What you usually do is you write this as 10 plus minus 6.24. Yeah? It's a sort of, it could be anywhere between 3.76 and 16.24. Looks pretty lousy to me. So scientists came up with this fantastic idea. How do we make this number smaller without really cheating? Well, actually, we do cheat a little bit. So what we do is we use the standard error of the mean. And the standard error of the mean is usually abbreviated like that. And that is the sample standard deviation divided by the square root of the data points. So in this case, it would be 6.24 divided by square root of 3. And that gives you, say again? 1.97. Why don't I have this here? I trust you. 1.97. 3.6. Oh, yeah, sorry. You gave me square root 3. Yeah. So that's 3.6. Hey, tell you what. 3.6 looks much friendlier than 6.24. So I can give this result as 10 plus minus 3.6. But I have to tell people which approach I used. Is this here standard deviation, or is this the standard error of the mean? So I would put that as SEM here. And here I would put that as ST dev. It's just, it's just like eye gouging. Make results look better than they are. Bastards, them scientists. Are you happy with that? Do you get that? Fantastic. I shall see you on Monday. Have a good weekend.